Good morning, everyone. Today is June 24th, 2017, and this is the John Chappell Natural Science Philosophy Saturday morning science chat. So we've been going for quite a few weeks now. So first I wanted to just take a little pause to see whether I can get some feedback on how you think these video conferences have been going. And if there's any changes you'd like to see, or topics or questions or comments. So this is your chance to let me know what you think. Anyone out there got some comments about like the format of
the
talk?
message that announces the conference isn't going out. I'm not getting any email messages. When I go to the website and I click on the links, I get a 404 message. So if nobody's showing up, that's an explanation for it.
Yeah, we seem to be having some problems. The links are
some
being
problems. It's a pretty serious problem, in my opinion. I mean,
I see.
somebody says, "Can I go into the conference?" and they can't. They're not going to participate.
So did the messages for this conference go out? So you
didn't get one.
So how did you manage to find the chat link then?
Well, that's a good question. I had to hunt around a whole bunch.
Where did you eventually find it? There's
first off, there's no real announcement. It's just there. And then it says, click on this link. So I click on the link and it says 404 error. And then I went to send an email message to you and I get another 404 error. Okay, so now I'm kind of confused. I go look at my email. I get no message from the email. It says that there's a meeting or going to be a meeting. And so I'm assuming that most people would do like me, like I did last week, assume there's no meeting.
Yeah, here's Slobodan.
There's no meeting. Was there a meeting last week?
Yes, Slobodan.
Yes, I wanted to. My experience is actually that on several occasions when I wanted to connect by phone, it was too late. For example, I was 15 minutes late or so. It was not able. It was not possible. Then I would send you something like how about to enable, but I would never receive the reply. And the other hand, when I initially tried to access by the link offered, I was supposed to download Fuse. I did that. It did not work. But somehow, last two times, I was able just to click on the link that you provided and put my name. And after that, I got in, at least on second time or something like that. So kind of, I don't know.
Okay, well,
it's not that straightforward. I mean, it was not for me, but somehow I managed it.
All right. So today you're calling in, so you're not going through the application.
Yes, but just in case, not to be too late. So in the meanwhile, I succeeded to get also by the link. So my name is there already. I think here Slobodan Edic, right? But
all right.
But now I cannot activate my phone. Okay, I will try it in the meanwhile time. But last time I was not able to put it on my headphones and mic. So I kind of was prepared to, if there would be something on the screen, to be able to follow, but otherwise I'm on phone.
All right. So I have heard that, as people do sometimes have problems clicking on the link. Now, sometimes the messages for the meetings are being created either by me or by David DeHilster. And so I'm not exactly sure whether maybe some of those messages are being created incorrectly. It's fairly easy to, when we're replicating the meeting requests, to not update the actual meeting ID, because that changes every single time we have a meeting. So, but I should probably think about some way of having a more reliable way of of announcing what the link is, I suppose.
I think that if we just had it on posted on the website and that link on the website worked out, well, it should be adequate. But I just basically followed the link that was in the email that was sent from the address that I posted in the chat section there. And I'm not exactly sure where that particular address is linked to, but I received that email, and that's the one I follow, and that's where it seems to work the best for me is following the link in that email.
Oh, you got an email, did you?
Yes, I did get an email to my registered.
When did you get an email? When did you get an email?
It's to my registered email address on the CNPS site.
Yeah, everyone, if you're registered, should be getting an email.
Yeah.
I got an email yesterday and today. Just at the start of the meeting, I got also a second email.
Correct,
So,
yes.
But also I got a similar email yesterday with the same proper link. So I don't understand the problem.
Yeah, let me share what the message that you should be getting. So Harry, I'm not sure why you're not getting it, but it's maybe you're not in the list or something. I would be surprised. This goes out to the, let's see here.
Yeah, I got one yesterday at 4:17 p.m. and the other one just at 7:59, which was 1 minute before the meeting today, just like Hans had.
Yeah, so this is the meeting link. This is what it should look like, Harry. Now, if you're not getting that, then I can probably check to see whether your email is on the list. But this is the way it's supposed to work.
I think you're misunderstanding the problem. When I went to the website, they're giving me links that give me a 404 error. Why is the website giving me a 404 error?
That is something that probably needs to be addressed because I get that same thing when I try to use the website.
I see that for some odd reason it's sending these messages now to the spam folder. But you shouldn't have to check the spam folder. I mean, I was receiving the messages regularly until last week, and now suddenly it's putting them in the spam folder. So I don't know what's causing that. But, you know, there's a lot of people out there that are not computer sophisticated. They're not going to figure this stuff out.
The reason that things are landing in the spam folder is normally that there is no subject field in the message. If there is no subject field in the message, then very often it's directly put in the spam folder.
I don't think that's really necessary for us to diagnose that. The issue is that I usually go to the website and look at the website, and there's a meeting announcement, and then I click on that, and that links there are not working correctly.
Let's see here.
Yeah, there is a subject field in this particular email for sure.
Yeah, whether it goes into spam is the function of your email program. Like if you're using Yahoo, if things are showing up in the spam filter, you can tell it to tell it certain mail is not spam, and then it'll show up. But let's see here. Now, normally the conference actually isn't announced on the website, I don't think. Let's see here. Someone's really feeding back here. I have to find out who that is. I think that's Pal. Okay. Yeah, if you're not talking, please mute yourself so we don't get feedback. Let's see here.
The other good thing is to use
there's this link here. It says join live video conference. So if you click that, that is not working. I mean, at the risk of breaking things, I'm going to see what it does. 694. No, that looks like the correct meeting ID, but you're getting a 404 when you click that. So that seems to work okay for me.
Right, you have to follow it beyond this point before it gives you the error, I think.
Do you?
Yeah,
It normally launches Fuse right at this point. But I'm just checking to see whether this number here is
Listen to
correct.
what I'm saying, Franklin. There are people out there who are not that sophisticated who don't understand this stuff. And if I can't figure it out and have a problem, there's going to be other people who can't either.
Well, it's just that it seems that that problem is a problem with a particular to your computer. And unfortunately, there's not too much we can do about that.
No, pay attention. You don't pay attention. Gosh. Blaming it on me isn't solving your problem. Your problem is you want people to participate. And if people can't figure it out, they ain't going to participate. Got it?
Yeah, I got it. But if people have computer problems, we can't help that either. So.
Yeah, I think in some senses it
That's
might be.
an excuse, Franklin. Stop making excuses.
Well,
if I provide the correct link and when people click on it and they get a 404 error, there's nothing I can do about that.
You're making an excuse, Franklin.
I think Franklin is right.
Yeah.
I think Franklin is just blowing smoke and making excuses.
You are making a big buzz.
Other people are having a problem too. Okay, do you get
Shouting doesn't help.
Yes, but you're not listening.
Okay. All right, you have to raise a flag here.
No, that's quite all right. I mean, I know that frustration, but this is more like a computer problem. But now, aside from difficulties on getting in, so I'm glad you guys all managed to find your way into the website. You know, I do get some feedback about, you know, some people come to the meetings and you know, they stay for a while, but they leave, and sometimes that's because some people are dominating the conversation. Now, sort of my opinion is that I'm here to get people to talk, and it's kind of hard to get people to participate. So you know, I basically let those people talk because they're providing content. So, but I was kind of wondering what you guys think about, you know, how the conversations have been going.
Franklin, I've suggested in the past, and I don't know, you said we could probably just let it run and people talk, but I'd suggested in the past we use more of the raising the flag system just to avoid the interruptions of one person to the other, and try to do things sequentially like that. Maybe we have something that says that we have kind of a time limit on the responses too. And I'm just saying it might make the meetings go smoother. Just a suggestion.
Okay. Let's hear. So I've got an echo going on here. There you go. Yeah. So once again, people need to mute themselves if they're not directly talking. Yeah. Sometimes the conversations can get a bit heated, and people start to try and talk over each other. So that is definitely my job as a mediator, to either step in and try and stop that. But to a certain extent, it's a little bit cumbersome to have to always raise your flag and stuff like that. And I think it might discourage some people from talking. But I will keep that in mind.
It might also just, you know, there's also people that call in by phone, and I don't know that they even have the ability to raise a flag then.
Yeah, probably not. So probably I will continue to just let people talk. But definitely, if you do raise a flag, I do see that, and that will eventually stop these other people. I mean, I think the usefulness of the flag is if you want to speak, but, you know, no one's letting any like air between sentences, feel free to put up your flag and I will stop them. So I think maybe we'll try it that way. But how about the topics that we've been bringing up and how we bring them up? Has that been okay with people? I see we have a new person, Yegor, but he doesn't appear to have a microphone. So welcome. All right. Well, if there aren't any other more comments, if you have any other comments, please feel free to send them to me at franklinhu@yahoo.com, and I will take those under consideration. So let's get to the regular main part of our meeting here today, which is our science chat, which we get to talk about anything that that you guys are interested in. So the first thing I normally do is find out whether there is something that anyone would like to discuss in particular. So I see we have some new people, like, is that Boff Fritzus? I think he's new. So Boff, did you have any topics that you would be interested in discussing this morning? Any burning science questions we're here to discuss? And I see we have Lou. Lou, you haven't spoken very much during these conferences. I was wondering, did you have any topics that are on your mind? No. Okay. Well, I did have some topics. That we could start going over that may be of some interest. And the first one I had suggested is looking into the areas of alchemy. Now, this is an area of personal interest to me, as I've actually done some of this type of experiment in alchemy. And actually, alchemy has a very, very ancient history, and people like Newton were actually alchemists, and they were trying to transmute things like lead to gold, or to come up with what was called the Philosopher's Stone, which was a great thing because it was able to convert theoretically any substance into gold, and it was able to give you extend your life, apparently. That was of interest. So do people here believe that alchemy was that just a gigantic waste of time? And does this have anything to do with science? Or do people think that it may be a possibility?
It's done in every nuclear reactor. Their atoms are changed in other kinds of atoms.
Yeah, we've definitely been able to do that in the modern sense with accelerators and with nuclear reactors. So you can turn like lead into gold using nuclear reactors. Now the only problem is that you can only create microscopic amounts, and it's not economical. It costs like $100,000 to create like a speck of gold. So
stars do that for you.
Yeah, stars may be able to do that for us, but they're a little bit inaccessible, I think. So I think there's a problem with alchemy in that even if you could do it, you'd have to be able to do it in an economical sense, meaning that you could make gold for less than the price of gold. So Corey, I see you raised your flag.
I got a conversation going around, so I'll just wait for a little while.
Sorry.
Okay.
Franklin?
Yeah.
This is Bill Lucas. There are some companies that go around to nuclear power plants, and they have waste, nuclear radioactive waste, and these people use an electromagnetic process to convert it to something that's not radioactive, that's valuable. And they like to do gold, platinum, iridium, those type of things that have a value. They are paid handsomely for getting rid of it, and they get to keep and take away all of the stuff they convert. So they make money twice. They make money in getting rid of the radioactive material, which they pay handsomely for, and then they also get to sell the materials that they make. And so that's a process that is dangerous in the sense that you're handling a lot of radioactive materials, but on the other hand, you can make some money.
Yeah, now I've heard about. I mean, these are stories on the level of like internet folklore. So I'm not sure what your sources are, but I have heard similar. I've heard similar stories and worked with similar people. And that was actually my introduction to alchemy. In that here in Seattle, there's like a meeting of amateur scientists hosted by Bill Beatty, and I met this like this old guy. He called himself Merlin, basically. And he claimed to be able to do all this transmutation stuff. And one of the stories he was telling me was that about things like nuclear waste, that basically you could deactivate nuclear waste by just pretty much putting it in a ball mill. So you just sit there and put the waste in, and you just sit there and you grind it up, and after a while it becomes non-radioactive. And you could get rid of nuclear waste that way. And apparently they were able to demonstrate this, and they were thinking they would do something like just bring in like a concrete machine and the giant ball mill and just throw all the nuclear waste in there and just let it roll around there until it deactivated all the nuclear waste. But apparently, see, no one would believe them. Even if they could demonstrate this, apparently, absolutely no one would believe that this would work. And therefore, no, they never did it. So this is
the evidence is available. For instance, at NIST, they measured the properties of all your radioactive isotopes to 8 significant figures. And when they did that, they were able to show that there's no strong interaction in the nucleus and there's no weak interaction force in the nucleus. It's only electromagnetic. So once you have that, then you can figure out how can I trigger the decay of certain isotopes to something that's stable and valuable. And so that's the problem. How do you trigger it to do that? And since everything is governed by electromagnetic forces now, although publicly you don't see that, but on the website for NIST, if you look at the data and you analyze it, you'll see that's the conclusion of the new data. But anyway, so what these people do is they devise a device that can take the most highly radioactive molecules or nuclei that are in nuclear power plants where they're doing uranium. And of course, uranium decays to all these heavy metals like gold and platinum and iridium and things of that sort, which have a very high value. And so that's what they do. And they have to convert it while they're at the nuclear power plant, and then they're allowed to take it out in a truck when it's no longer radioactive. And so that's what they have to find a way to get everything to decay much faster than normal, and then to separate it out into the metals that they particularly want to keep. And so being a nuclear physicist and having worked in this field, to some extent, I'm aware that they can do it, but they have a secret machines that they have developed that they're not patenting because they're the only ones that can do it. Many power plants will not let them come because they don't believe it's possible. But the power plants where they have been successful, they invite them back. And some power plants, will keep their radioactive material for 50 years because they don't know of any way to get rid of it. And so they become desperate after a while for something that will help them to get rid of that radioactive material waste.
Sounds like the people at Hanford over here should talk to those guys. They got plenty of radioactive waste. But you're saying that they actually have to process it near the nuclear reactor, which is
they have waste kind of like lakes, ponds and things like that, where they store their waste at these nuclear power plants. You have to go in and pump the stuff out of that and process it. And then they take meters and they measure how much radioactivity is left. And you got to get below a certain level or you cannot take that waste out and you cannot be paid for getting rid of it. So it's very scientific in terms of the measurement of the waste. But what is kept a secret is how to do it electromagnetically. We know that they use electromagnetic processing. And so the trick is, how do I trigger a radioactive nuclear isotope to decay faster than normal? I mean, things like uranium decay in millions of years. So you gotta find some way to make some of these things go faster.
So, because that sounds an awful lot like the situation they have over here in Hanford, Washington, where they have these gigantic sludge waste tanks. And so it may not rely on the presence of a nuclear reactor per se. I was reading up on this, and they're saying that there was some experimental reactor in Russia which had this lead shielding, and somehow that shielding had turned into gold. So
well, I would be a little surprised at that because what you're doing here is you're changing a non-radioactive material into something else. That is not what these people can do. These people can merely channel the direction of a radioactive decay to get it to the final product that they want that's not radioactive. So you have to be able to trigger the decay process to go in that direction. So if you were to look at, for instance, from uranium, there's probably 40 or 50 elements that it gets to on the way to lead. And so you only want a few of those. The rest you don't want. And most of them are radioactive all the way down to lead. And so you've got to have some way to alter the decay path sequence so that it doesn't keep going to radioactive materials, but goes to something that's an isotope that's not radioactive, that has some value. And that is the trick to do it. And because electromagnetic forces are governing all aspects of the decay, you know that if you can figure out what kind of fields or forces to put on these to control that, then you could have some success. And since the politically correct scientific community doesn't work on that, they don't know anything about it. So if you go to some place like Hanford, which has a lot of experience, they may say, well, we don't believe in this.
Yeah. So why is it that they won't believe in it? What is the main sticking point?
Money.
Well, if it was money, people would just flock to it because they love money, and getting rid of nuclear waste would be money. But I think it's more of a science thing that most people just simply believe that transmutation, without nuclear reactors and such, is simply impossible, right? Like I said, in the story that I heard, basically they could clearly demonstrate it working, but someone higher up just said that that's just not possible and dismissed them.
Well, you see, in all the textbooks for nuclear physics, they don't recognize the new data from NIST that shows that you cannot have a strong nuclear force or a weak nuclear force in nuclei. And the reason that they just been able to do that is when we invented these ideas of the strong force and a weak force in nuclei, we only measured the properties of nuclear isotope to 4 significant figures. And there was a certain amount of uncertainty there that allowed us to generate these new ideas to explain nuclear decay and what holds the nucleus together. But then when we went from 4 significant figures to 8 significant figures, we removed all that wiggle room that would allow you to have these other theories. And what you can do is you can analyze that data in such a way that you can actually plot the force within nuclear isotopes that is holding them together. And you can see it's a 1 over r squared force. And there's no way you could have a 1 over r cubed to 1 over r to the 5th, which is what the strong interaction and the weak interaction use, because they're ruled out by the data. And it's not one piece of data, it's 3,500 nuclear isotopes data that rules it out. We don't know of any nuclear isotope where the strong interaction force or the weak interaction force could exist now. And but you know, we talk about alternative science and stuff like that. Well, NIST is under pressure because they paid for the money to have all these measurements made. And they put it on their website, but they don't put it on an easy way to see it in this manner. They put it on by just element number. So like if you have...
Well, do you think that NIST was expecting to see the 1 over r to the 5th force and the 1 over r to 3 and then declare there's a strong force?
No, they were not expecting to see it. And the people who first reported it were at the Fermi National Accelerator Lab near Chicago. And I think they were all fired for showing that. And so that's what happens. There's a lot of money involved here. And this would enable a reduction of costs and a reduction of grants for people who are working in the nuclear industry, and they didn't want that. I used to work for the government, just to give you an example. I was making supercomputers, and they cost $8,000, whereas regular super-cooled computers like Crays and stuff like that cost hundreds of millions of dollars. But my computer was more powerful than they were. Did the government want that? No. In fact, they told me, if you don't leave government service, we're going to fire you because we don't want low-cost computers. We want to make huge profits on awarding of grants and contracts to buy these big computers for computer centers. And I had replaced over 500 computer centers in NOAA, many of which had $100 million or more of computers, with one $8,000 computer. And they did not like it because the people who were in charge of the computer centers were no longer getting kickbacks of millions of dollars a year. And, you know, that they told me, you know, this is not the way we do business in the government. We don't want to do business this way, and then we're going to get rid of you. And so I had to leave NOAA. And so that's going on in the nuclear area. It's going on in the medical area. It's going on in many aspects of our government. And it's a shame. I don't think it's good, but how are we going to stop it?
Yeah, those stories you keep on telling them, and they're kind of hard to believe that, you know,
not
stuff
if
like
you're
that
the one
goes
who
on.
had to leave and get a job somewhere else.
I see Cornelius has raised his flag.
Okay.
So you had a comment?
I was just wondering why Bill didn't sell those $8,000 computers to Bill Gates, because I think he would have loved to have that kind of computing power.
I knew Bill Gates very well. He was not interested at all. He understood how the system worked.
Okay. So there's a clue there too. Huh? So
Yes, and
it's all
also Steve Jobs. I knew him very well. We spoke often at the same computer uh, meetings. And
okay.
like we would do the Federal Expo in Washington, D.C., we would do the NIST computer science conferences. And, uh, and there was a lot of news wondering why no one liked what I was doing, because from the general public's point of view in those days, we were just wasting our money.
Yeah. Okay.
And
Well, I just thought I'd ask because it just kind of adds to what Franklin was saying. It's very difficult to comprehend how this could all be happening and not be out there being sold privately, or how this nuclear waste could not be being so cheaply converted that everybody isn't making money. Things that make money usually don't stay silent. They require a lot of government intervention to eliminate physically the people that are aware of those things. It's just difficult to fathom. Plus, like Hans says, basically nuclear energy is converted in stars, and you pretty much have to create a star-like condition in order to convert the atomic core to different.
That Large Hadron Collider is trying to imitate somewhat what stars do. And I think what you need is very high gamma radiation, very high energy gamma radiation in order to start or trigger atomic reactions.
Right. So otherwise,
Then you can speed up the decay of the nuclear atoms.
yeah, otherwise we're talking like cold fusion or something like that. Uh, and so far, that's not, been in the picture as far as I know, and I don't see any reason why it would be. It seems like the only way you're going to create and control those types of things is in a strong gravitational field that stars create to contain the reaction, or to concentrate the reactants so that they can react. Otherwise, you're kind of just stuck waiting for the normal lifetime decay of the nucleus. And if you do concentrate it, somehow you're going to wind up with so much excess energy that you won't, from the nuclear interaction of the nucleuses, that you're going to not be able to contain the excess interaction. You're basically going to have a meltdown of your system.
Now I see we have a few flags from Hans. Did you want to have? Do you have some comments here?
I just gave my comment.
Okay.
Very large computers that can be put together are called grid computers. They are sets of PCs, in fact, very small computers that work together. And they are used, for example, to build large movies. Shrek, for example, is generated by such a computer.
Let's hear. Jim just sent a link here about someone who's got a patent on low energy nuclear waste remediation. So this is actually an area of significant current research, and they call it low energy nuclear reaction. So unlike what we think what might be necessary, which is all this like in the sun kind of high energy nuclear transmutation, these people are trying to do things at a very low energy level. And there have been people who have been saying that they can generate a substantial amount of heat energy using things like a nickel and hydrogen kind of fusion type of thing. And apparently these guys have got a whole patent on something using palladium. And of course, we had the whole deal with when it's Hans and Pointman or whatever those guys were, with their cold fusion claims that they're able to do fusion just by running electricity through electrodes, which are all basically still kind of alchemy things. So alchemy is not dead, it's just gone in kind of these different directions here. We'll call it cold fusion. Now, I've done some work in cold fusion myself, and I have videos, for example, on my YouTube channel, where I do some of these experiments. Let me see if I can bring up one of those. For example, one of the most dramatic demonstrations I have is basically creating iron. So you start out with carbon, and you just spark some carbon rods. And what happens is that after you do that, you can use a magnet and you can extract out these little iron filings. And now the basic contention here is that there are very, very few magnetic elements. And so if you can create anything that's at all attracted to a magnet, then probably you have created iron, most likely. So let me see if I can dig up that video for you. And let's see here. No, let's see. Now the other experiment that I have was actually trying to do the gold transmutation experiment. Now the theory there is that basically atoms work in basically octaves. That if starting from copper, you can add enough electrons to get to the next row in the periodic table of elements. And then from copper, you can go to silver, and from silver, you can go to gold, is the basic progression. And basically, the way you do that is pretty much lighten up a coffee can full of gunpowder. So it's just a very energetic chemical reaction. So let's see here. This is one of my original videos here. Okay, let's see. Let me share this video. Okay, so this is a very simple experiment. Now, you guys can't hear the video, I don't think, but I just used some pencils here and attached some alligator clips to a regular little 12-volt battery. As I just sparked those. So let's go forwards here. So you just do that. Okay, so that's the results. And then I just bring out a magnet and I see whether that attracts anything. So it did pick up some little black specks there. So something did get attracted. And then I try and move the magnet around. So I take those little specks away. And then I'll run the magnet underneath the paper to show that there are magnetic specks in there. So I don't think you might not be able to see that, but there are the little specks that are following around.
Were you able to check if your pencils are really only using carbon?
No, actually, that's a significant problem because most pencils are actually manufactured with a significant amount of iron. So that was my first attempt. Of course, that was the initial criticism that I didn't know whether there was iron. And now the thing is if you sit there and you grind up your pencil and you do basically the equivalent test without sparking, with fairly weak magnets, you still don't pick up anything. But with powerful rare earth magnets, you do pick up stuff. So that was the other problem. In order to eliminate the possibility of there being iron, you need to use the stronger rare earth magnets. So I did a second experiment where I went and I tried to buy the purest carbon rods I could find on eBay. And even then, if you ground this stuff up and run a high strength magnet over it, it will still pick up stuff. And so the main problem is I could not find an iron-free carbon source. So what I did in my second experiment is that I had to basically make an iron-free carbon source. I had the least amount of iron was in like this graphite powder. So that should basically be pure carbon. But even that, if you ran a magnet over it, would pick up these magnetic particles. So what I did is that I took my sample of graphite and I ran the magnet over it, and I ran it over every time extracting out these iron particles. I kept on doing that until no iron particles remained, so that at least in the sample that I was working with, there was no detectable iron. And then I did my sparking experiment and showed that suddenly a very, very large amount of magnetic material appeared after the sparking. So, but that was, there's still significant room for doubt as to how pure things were, since I don't have a spectrograph or whatnot. But the point here was that, that's about as close as I can do to do this experiment in a experimentally rigorous way. But my other point was that these experiments had been done at universities by Professor Jim Brockris using, spectrographically clear carbon. So he was able to do a much better job than me, and they were able to find this iron as well under scientific conditions. So I believe that, yes, I was able to create iron during these experiments. I was not able to do it scientifically rigorously, but other people have been able to do it scientifically rigorously and have, published papers on it. So I see Corey's raised his flag. Yes, you have a comment? I think you're still muted there, Corey.
Yeah, okay, sorry. I was just noticing that Lou is making comments and Slobodan is making comments that Slobodan can't get his microphone to come up, and Lou says she can't seem to unmute herself. I believe when you tried to speak to her earlier and she tried to respond, but her microphone wasn't working, because I heard a faint glimmer of Lou's voice in and out when she asked. And she just now unmuted herself according to the image, but I don't think anybody's hearing her, right?
Okay, well, I just unmuted you, Lou. Can you talk, and can we hear you?
Can you hear me?
Yes, we can hear you, Lou.
Oh, okay. Well, that was my problem before. I'm just happy to listen. I find this very interesting, and if I have something to contribute, Did you would you have to unmute me? Is that the issue?
No, I don't think so.
Because I kept
But
trying. I was clicking and clicking and clicking, and it would just it went to unmute and anyway, it was just going around and round and round and round and not unmuting. So,
okay. Well,
but
if you raise your flag, I'll make sure you can comment.
Okay, could we try, is there anything you could try and see if Slobodan can be unmuted on your end? Because his microphone isn't even showing, but he's having trouble. Do you see one on
Okay,
his
well,
point?
Slobodan is one of the Collins, and so I just unmuted somebody. Slobodan, can you talk? Or I'll meet the other telephone number.
So you don't hear me, right?
Okay, we hear you, Slobodan. You're the
Okay, all right, good.
caller.
Okay, maybe later then I jump in at some point. Thank you.
All right.
Now, he can also not raise his flag, so you might have to look at the comments column to see if he's making some kind of gesture saying he'd like to speak.
Okay, I'll try and monitor the group chat here. Yeah, if you want,
Okay.
you want to speak, raise your flag or put something in the chat.
Okay. Thanks for your help, Franklin.
So, but what do you think of that about converting carbon to iron? So, does that work? Was that convincing?
Yeah, personally, like I said, I don't really consider any possibility of converting one atomic type to another atomic type of atom without change. The nucleus has to be changed, and the nuclear change is a rather energetic interaction, as far as I'm aware, and as far as I can. My theory fits together too with it. It has to be a really strong interaction, and it's not just simply, ionizing the atom.
Well, I think that brings up the main point that we're trying to talk here about these alchemy things, is that is in fact the mainstream attitude, that even though we can do experiments which can clearly demonstrate some kind of transmutation here, that still people refuse to believe it. I mean, is that how you feel about that? That even though you've witnessed some experiment, and let's say that I showed you the university result in a published paper, clearly showing this is what the parts per million of iron was prior to the experiment, and this is the parts per million after the experiment, and it's like 100 times more.
I would have to say I would be very skeptical about it, and I don't know. You'd have to see exactly what the experiment was and how they isolated it from the outside world, that the iron couldn't have impregnated the material of the experiment from other sources. I'm not that versed in atomic reactions, and that is just from a logical standpoint, it just doesn't make sense that that the nucleus could just change on its own.
But why do you
But
feel that's illogical?
There's always statistical possibility that a small, minute interaction could occur. Because
Well, I'm just trying to get at, because you actually represent the mainstream view on this. I mean, probably if we all got in a room, all the people would be on your side of the room, and there would just be me and Bill on the other side of the room, saying that we don't believe that nuclear reactions are possible. That would transmute, say, things like the claim is that the carbon and the oxygen get together and they form this iron atom. It would take like 3 or 4 carbon and 2 or 3 oxygen atoms to actually get there. So not only would you have to have like one fusion reaction, you would have to have like 3 or 4 simultaneous nuclear fusion reactions in order to get to iron.
Right, you'd have to see the bonding energy coming out of that type of a reaction, and you wouldn't see that bonding energy. You know, you're not seeing that kind of bonding energy, so I don't think that the reaction is occurring.
Even though you see that scientifically, you can see the only thing that was in the input was carbon and iron, and the output we see iron that wasn't there before.
Well, scientifically, I don't see that. So, I mean, it's written in a piece of paper, and there's a lot of stuff that's written in pieces of paper. So I just, you know, it doesn't fit in my model. It couldn't happen in my model without creating an environment like a star or a nuclear fusion reactor where you have highly concentrated material under extreme heat or highly concentrated material under extreme gravitational pressure.
So what is it in your model? What is it in your model that tells you it must be that way?
Well, in my model, basically you have, since it's a stress-based model, you have to reach a point of the tension within the space being high enough that you actually have reached the point of what I call maximum tensile strength of the material, which is where things are, you're going from a negative feedback to a positive feedback in your oscillations. And at that point, you can actually acquire an additional oscillation or an additional cycle in the oscillations. And then when you've done that, you've created an additional atomic structure. So it's a model that's, like I said, it's based on waves, and it's based on tension, and it's based on basically a tension curve. So you have to reach that level of stress within the media, and that level of stress is only attained in a high gravitational field or an intensely active thermal field. So that's just the way it works in my model.
All right. Well, I think that's very different.
It seems to be, you know, consistent with the evidence so far that we found to where these types of reactions occur.
Also, what you call mainstream doesn't understand the nuclear reactions. They only can describe them very well. They have done a lot of these experiments and describe what happens. They don't understand what in fact is going on there. So how could you say mainstream is not believing this? Mainstream doesn't understand that either, but they have done a huge number of experiments, and they have done them very precisely. And you have played with two pencils and think that you can prove something. That's the complete love. The one against the other. It's no comparison.
Okay, sorry, I knocked my Wi-Fi antenna over. You were saying something, Hans?
I'm trying to tell that also what you call mainstream doesn't understand the what the nuclear reactions exactly are. They have done a lot of experiments and can describe what happens. That doesn't mean that they comprehend how the reactions go. They don't really understand the strong force or what is going on there. They have descriptions, and no process that generates or decays. They can describe the decay in terms of what is being observed, but they don't know the process that's behind this.
Right. So what you're basically saying, Hans, is they've got quantitative analysis and predictions and statistics predictions, but they don't really know the mechanism or the mechanics behind the reaction.
That's exactly so.
Yeah. So this is the standard picture of the atom, where we have the nucleus, which has all the protons and all the neutrons in the center. And then we have all the electrons kind of, you know, orbiting around the nucleus. And the nucleus to scale would be a dot so small that you wouldn't be able to see it, basically.
Right, but that's
That
basically an idealization for representation or their quantitization. They also say that it's not really those little balls rolling, spinning around or clustered together. It's basically that's the different amounts of packetized energy they see coming out in the quantitized characteristic, but they don't really know what the real physical structure or layout is. And I, like Bill and some others, believe it's more of a wave structure, and there really is the discrete components or discrete little balls that you have to worry about their specific position. So that's more of basically an image of their quantitization or quantitized value components that they see come out, and it's not necessarily what's truly there. And they're aware of that, and they even will tell you that it's an electron cloud. They won't tell you that it's a little concentrated charge particle running around in a circle like that description there. They will say
yes, this is the cartoon version of the atom, I would have to say.
Yeah, it's the modeled version. Basically, as it gets to quantity, and like you said, it's not at all to scale because we couldn't even see it if it was actually drawn to scale.
But see, the problems here is that we have all the protons in the middle of the atom. And the problem there is that all those protons would want to get away from each other. The nucleus should immediately explode because of the massively imbalanced forces. But the mainstream says, well, there must be this incredibly strong force that keeps all those protons in that tiny little ball there. And this strong force is like super strong within the radius of the nucleus, which is super tiny, but is zero outside of it. So that would be like the problem with the strong force.
Well, again, the little ball is just a depiction. They're not saying that it really is a little ball like it's shown in a picture. But they are saying that to keep those positive charges together, and those positive charges interacting with each other, there is a strong force that keeps them interacting with each other.
Yes, that's what they say. But getting back to what Bill reported, is that if those protons were held together with this strong force, which would not be 1 over r squared force, it would have to be, like you said, 1 over r to the 5th, that would be reflected in the basically the energy differences between isotopes. That because these things would be bound together with this stronger force, it should show up in the energy mass balance. But what Bill is saying is that there isn't any evidence of the strong force. That there isn't any evidence that there's this 1 over r to the 5th force present inside the nucleus. There's just simply no evidence for it.
Yeah. Yet this force comes out when we do split the nucleus. And Bill's also saying the neutron doesn't exist separately within the nucleus, and I agree with that. I agree that there is no separate little red balls like they show in the picture, and there's no little separate blue balls like they show in the picture. There is a component or equivalency of charge and equivalency of mass that can come out when broken apart into those discrete sizes. But there is not necessarily any discreteness within the nucleus, in my view.
Well, I think the main point I'm trying to make here is that the reason why people think that transmutation is generally impossible is because the nucleus is so tightly bound and so tiny, it's inconceivable that you could break that thing apart and rearrange it or add something to it or take something out of it without a great deal of energy. And normally the most common transmutation would be, for example, when we try to do a fusion reaction, and we know that that takes normally a gigantic amount of energy. I mean, they have like these tokamak reactors where they're trying to do these fusion experiments. and it takes just an insane amount of energy to get these atoms to fuse. So if that's the case, then how is it I could have possibly fused together some carbon and oxygen atoms using nothing more than a 12-volt battery? So we're talking about energies here which are not really above chemical reaction energies, very, very low energies. And that's what these low energy nuclear reaction people are claiming, that they can perform these fusion reactions at extremely low energies.
Okay, if I can give a quite a small example of perhaps a visualization of the way I would do it, be like, if I may.
Yeah, go ahead.
Okay, if you have a, let's say the ocean, for instance, and you have a retaining wall within the ocean, and there you have waves going on both sides of the ocean, and you say on the one side of the retaining wall, you've got a very small closed area that waves are just oscillating back and forth within, and on the other side of the retaining wall, you have the entire ocean. In order to get like a nuclear fusion reaction where the smaller area of the retaining wall, the smaller area of the pond, or if you will, that's enclosed by a higher wall. In order to get any additional activity into that higher wall, what you're going to have to do is accomplish either getting much greater waves on the outside of the wall that can go over the wall to add to the energy that's within the container, or you're going to have to raise the entire level of the ocean. And those are kind of like equivalent to increasing the heat intensity. You would be like increasing the wave intensity and a wave activity outside in the ocean, or like increasing the gravitational field and the gravitational energy outside in the surrounding space, as if to raise the entire ocean's level so that the waves that are on top of the ocean can then again go over the wall. But you need to get that extra cycle of wave inside that barrier, and then you've got an additional wave that's interacting with the other waves. And that's kind of like how I would spontaneously reply to how a nuclear reaction would occur to increase or decrease the content of the nucleus. It's just it's an ad lib thing, so it's certainly not a literal by any means, but it gives a conceptual idea of how the waves are packetized. You have to actually create the environment for that reaction to occur, and which would be basically raising the level of energy of the entire ocean, or increasing the intensity of energy within the surrounding area to make it break that barrier.
Yeah, well, I think that's sort of how the mainstream sees it, and they see that barrier is so high that it's inconceivable that a 12-volt battery could possibly break through that barrier. But yet we have an experiment where apparently that happens.
Yeah, you do have such a thing as like even in the ocean, you do have such a thing as a rogue wave, where a whole bunch of wave patterns will combine together, and all of a sudden, where there wasn't even where it was a very calm ocean, you got this huge, huge 20-foot wall of water coming at you because all the waves combined, and until they all combined together, you couldn't even see that there was hardly any waves there. If a condition like that occurs, like say for instance near this barrier wall, then it's conceivable that at that point you could have what you're saying as a nuclear fusion. But you have, in order to create that environment repeatedly to change a volume of atoms, you would have a problem. But you could change an atom on occasion statistically, just like you can statistically occasionally get a rogue wave in the ocean that you have no clue that it's coming.
Mm-hmm. Let's see, I just got a link, an interesting link. So this is a reference to the experiments that I was referring to, and this is done at Texas A&M University. So I believe this is just a general summary of the experiments that were performed during that time, and some of them involve reduction of radioactivity, some of them involve the carbon to iron, and some of them involve actual experiments to transmute the elements to gold in very high, in what would be like a high value transmutation. So if people want to, they can take a look and see what's in this paper. But there are more scientific papers, and I believe like the people that I was talking to, like Merlin, so like this is a radiation chart here showing counts per hour going down. I believe like the person I was talking was actually in contact with these people. So and I've done some of the experiments where they basically take basically a gunpowder kind of thing where it's a potassium nitrate and carbon, and you put in some base metal, and then you ignite this thing, and then then you measure the amount of gold present afterwards, and they seem to be coming up with a increase in the gold content. So in fact, this is like a recipe ingredient for what they use. They got carbon, potassium nitrate, sulfur, and there's some lead and some silver, some nickel, some palladium. So they would mix all this stuff up and light it up. And they would
look like
they
an
would
interesting
see.
article. This is the link by Jim Marson there.
Yes. So
okay,
just take a look at that. I like this. The reaction of the University of Philadelphia project was at first silence, right? Because it's like they're all shocked. It's like, can't possibly be. Except Corey's reaction is exactly the reaction that everyone would have, is you did what? And then followed by, I don't believe it, and please go away. So
yeah, I think the thing is that it's difficult is, under this rogue wave scenario, it would be difficult to see how that could create a jump of several different atomic nuclei levels. But if it happened to occur between a couple of different specific nuclei patterns, it still seems difficult, because you would have to strip away the electrons to make room for the reaction to occur between the two nucleuses. It's kind of hard to comprehend, but certainly with the details that are going on in this type of reaction, it's difficult to just say, to understand exactly the sequence that's occurring. Statistically,
well, I think all of that is really pointing to that probably your understanding of the atom must be wrong. If your understanding of the atom doesn't allow you to have these kinds of reactions, then, unless the experiment was wrong, then there must be something massively wrong with your understanding of the atom.
Well, except for if you look at the number, the amount of reactions that occur in that, and statistically the possibilities, and that, there's not the understanding of the atom as far as that goes is not that big a deal. But what's in complex is that we're not talking about a hydrogen atom versus a hydrogen atom, which is already a difficult scenario to make calculations to down to the specifically what's going on in the interaction between those two. When you get to these more complex atoms, there's a very, very sophisticated geometric pattern that you're talking about that's interacting with another very sophisticated geometric pattern. And to do those calculations or do that simulation is what's extremely difficult. And then to introduce the right amount of random rogue wave characteristic into that environment to cause this reaction. Those types of things are difficult to predict. The fundamental characteristic of what it takes to build an atomic pattern of a neutron, an electron, or a proton are not that difficult, but from those fundamental characteristics, you have to build up to much more complex structure of these other atoms and see how they interact. And that's
Let's
what
see.
becomes difficult.
Yes. Well, I'm showing this. So this is the conversion of carbon to iron section here. Now, it is a little bit funny that there was so much excitement from Pons and Fleischmann about fusing some helium atoms, but it's like I would say, like, so what? I can fuse I can make iron, right? It's like, and that's much bigger atom than fusing tritium. But unfortunately, I would say that as groundbreaking as that might be, you know, the end product of the fusion is like iron, and no one's going to make any money off of iron. And it would seem that the energy of the reaction is thrown off mostly as photons, as mostly very, very brilliant white light. So it's a very clean fusion, as it doesn't generate a lot of nasty like gamma rays or beta particles or the other nasty kind of radiation we normally associate it with radioactivity. It just throws off a huge number of electromagnetic waves in the form of very, very brilliant white light. Now, one of the things I've kind of pointed out that may be this being used in a practical way is in carbon arc lamps. So, I mean, that the carbon arc lamp is exactly the same experiment I was doing, except that you're just harvesting off the ginormous amount of light that is being generated by the carbon arc spark there. So my assertion is that the reason why that generates such a huge amount of light, and it's been shown that that light is not due to the incandescence of the carbon rods. I mean, the spectra is just wrong, and it's got an awful lot of energy in the UV range that just shouldn't be there. That what you actually are seeing there is a fusion reaction, and the brilliant white light that you see is the release of the energy of that fusion reaction. So my only questions is that if you have these carbon arc lamps and you take it out of an oxygen environment, does it still work? I would contend that it probably doesn't. Probably you just get a dim spark like you would in like I forget what they call it, but you know, just a dim spark, and not the super brilliant light that we see. But that might be the practical application of fusion energy.
Why would you say fusion reaction? Though, what indication is that there's one type of matter converting to another rather than just an electrochemical reaction?
Well, it's from the carbon to iron experiments. You know, we know that we sparked carbon rods together, we get iron. So that's a fusion reaction, and that's exactly the same reaction as being used in these carbon arc lamps. So, I mean, where does that enormously bright light come from? If you spark like two electrodes together, there's no way you might get a nice spark between the two, but you're not gonna get like what you see in carbon arc lamp. It's just hugely bright. So that's just kind of a little mystery for you to think about.
Well, I think you get the same thing when you're trying to do a welding.
Well, you do as well. So even though some of those actually involve, but there are some other things that don't involve that. So, but that's just something to think about. That there are other ways of creating brilliant lights, but carbon arc is one of them. So let's see. There was some comments here. Someone's talking about moon dust. Let's see here. Yes, well, Lou was worried about if we did figure out how to transmute metals, that would devalue the price of gold. And actually, that's what was done in ancient times, and that alchemy was actually outlawed because they felt that it would cause a depression in the price of gold. Of course, that seems to be quite a reaction for a process which no one's really been able to demonstrate. But I would figure that the problems with alchemy is that you have to be able to make it economical. So like I was doing these alchemy experiments, and it would take me like 3 hours to grind up and prepare the materials for the reaction. And if I were to be doing this, it would just like the cost in hours and materials would greatly outstrip the value of any gold I could have possibly recovered. So even if it worked, even if I was able to make gold that way, it just simply would not have been economically viable, since the costs of all the materials and all the time and all the processing would simply be more than the cost of gold. But
Slobodan would like to say something there too, I see.
let's see here. Do I need to unmute him?
Yeah, he's on the phone.
Okay, I'm going to unmute you there, Slobodan. Okay, go ahead.
Okay, thank you. So I was listening to the discussions of, it's very interesting from the very beginning. Later there was some mentioning of the sparkling and so on. Actually, the point would be to produce the high gradients in the ether, and the sparkling is actually that mechanism. It's taking place apparently in the transmutation domain, but also in the over unity energy generators domain, I'll say. And here I sent two links just maybe quite some time ago, maybe just 1 hour ago. Up there is one link, and followed by another one related to questions and answers. There has been a guy, Puchta, maybe John or something, Puchta, who had very impressive presentations on Tesla Tech 2015 and 2016. I'm just uploading, and exactly in his system, they are kind of doing the transmutation of gold, kind of creating monoatomic gold and some kind of transmutation, some morphogenesis or something like that. Very, very impressive. And after that, I had a presentation that I referred to his presentation, pointing to the very small area where the sparkling was taking place, and the presenter did not pay much attention to that. And I really use it in support of my insights and my view that I had in my presentation that I shared with you some time ago. Here, on this paper that Franklin you just showed, there is also mentioned John Majulski or John Milevsky, as is his original Bulgarian family name. He has been doing a lot of stuff there. He was producing gold out of the glass and some sand and so in the microwave oven. And last year, or was it, last year, or maybe a year, 2 years ago, 2015, I think he was not there, or last year, actually, he was not there. Another guy conveyed his greetings to the group, and then he showed the first slide, and he said, try to guess what is this. It was big crater kind of shown on the slide, and nobody would respond. Okay, are you with me, Franklin?
Yeah.
Yeah, okay. And then he said, you will never guess. This is the place where John Majulski house used to be situated. So I mean, kind of, it was really impressive. So I'm uploading his old video. Was made at a conference maybe some 10 years ago by him, and when it is done, I will forward, send you the link. So really, in my view, I would not have anything kind of problematic here in terms of possibilities. Even principles could be kind of be seen, I mean, certainly very easily for me. Starting from the radioactive, cleaving, I mean, there it would be about emulating the situation that happens in the reality. Maybe some kind of isotropic homogeneous agents, energy agents, as ether could be, and you kind of are producing kind of brushing up of the structures inside, And then in that way you get rid of, or you stabilize the structures, the dynamically, stable orbital structures in essence. And I noticed that Bill Lucas mentioned something like 1 over r to the third degree, kind of attractive or repulsive force, in addition to 1 over r to the second degree, and so on. And then that falls in line with, for example, at least my insights about the universality of these two forces in both attractive and repulsive the first one related to electric field, the second one to magnetic field, and so on. And that this sparkling is something really very, very important. And if maybe next time the topic would be kind of over unity systems, then I would be maybe offering to lead you over some slides that I presented last year at Tesla Tech and so on. And then that topic or that aspect of exciting the system, the environment, the whole system, the structures and they how say substrates would be becoming pretty clear, I think.
All right. Well, thank you for the
that much for me.
Slobodan did put those links in there, so it seems like they're while alchemies may seem to be an ancient topic, it seems like it's quite alive in these over unity experiments, low energy experiments, and so there's definitely a fair amount of research going on there. But I suppose the question is if these kind of things are actually possible, then there must be something incredibly wrong about our atomic theories. And so as dissident scientists, we all have, well, some of us have alternate theories, but these alternate theories need to comply to like the new information that we have. So the new information that we have, well, the new information that we have
results like this, yes.
Yeah, we have results which are hard to explain. Things like the lack of strong nuclear force. So, I mean, that alone is kind of the death knell to almost all existing atomic theory if the strong force doesn't exist. Because then how can the protons possibly be held together by the regular electrostatic 1 over r squared force? That's just not possible.
You know how, Franklin, can you hear me? You know how? There has to be another force. If it is electric, gravitational, whatever, there has to be anti-attractive, repulsive force. Term it electric, magnetic, or whatever. Maybe electric and magnetic, it is just 1 over r to the r squared and 1 over r to the third. There seems to be those forces, I just suggested, for example, for you to put something like that in your simulation that you came up with regarding the Apollo structure and so on, So, I mean, if you have some structure, some conglomerate of some again, structures, right? They attract and repulse each other. So, at one point, you get actually dynamic equilibrium. So that combination of attraction and repulsion actually produce the kind of stable orbits, essentially, or maybe not that stable as is in the case of radioactivity. So,
well, I just
those,
don't.
The category of like strong force, then weak force, then electric, magnetic, gravitational. Those are artificial. They just apply to certain scales of reality. And there must be, everyone was looking into it in that way and expecting something like that. That very simple thing, that we have the same mechanism on all scales. So kind of, I think we could be pretty close there. I mean, I agree. And I had proposed long time ago in the correspondence on email, let's look into our unit systems, right? Let's try to explain them, support them. Otherwise, no of the theories can hold. And then today we had that issue of transmutation and so on. That applies as well to it. So unless the theory cannot support that and cover that, I mean, accept the results. Try to accept. Assume that they are working and try to still neither official mainstream, neither the alternative theories that many of you guys are coming up with seem not to be able to support that. Unless we allow for the pool of energy, in which everything is flowing and floating and out of which everything comes out and gets back in. There is no way to get something, kind of explanation for that.
Yeah. So,
okay.
like you said, we have we have alternative explanations. I myself have my own explanation for atomic theory. So, I'm just going to I'm going to stand on my soapbox here and explain a little bit about how I think this works. Now, I support the evidence that there is no strong force, that the only force that's holding the atom together is just the electrostatic force. Now, if you can accept that, then you can think that these low energy nuclear reactions can happen because you only have to overcome this electrostatic force. I mean, that's basically the same force that holds molecules together, right? So if the same force holds
but that force has to have its source, That force has to have its source. It has to have pool out of which it takes that kind of energy or whatever, out of which that force arises. The force is just kind of qualification. It's just conception, and the process is physics, something that is basic, So we cannot see. So we should not talk about electrical charge, magnetic charge, unless we know of what process that is a representation of. This is kind of just concept, just presentation. But we have to think and get into the process, the energy, the flows, and the relationship and the laws that they are obeying.
Let's not get too far off the topic here. Let's stick with atomic structure.
All or nothing.
Let's stick with one bit at a time. But we're talking about atomic structure and what kind of atomic structure would make low energy.
Just one get it. So I was talking about atomic structure, of course, or whatever structure, or whatever scale. So I'm not going to talk anymore. I mean, until the end of this session. So thank you.
All right. Like I said, I was going to explain a little bit about how I think atoms are formed. So first of all, I think that the Rutherford experiment that said that the atomic nucleus is this tiny little thing, I believe that is completely wrong. That, exactly what can you tell about the atomic structure by firing helium nucleuses at a thin layer of gold and then observing the backscatter? So what he observed was that he's getting these very strong backscatters, almost directly off, coming back at him, and the only way he could conceive of that happening is with a extremely concentrated positive charge to repel the positive charge of the incoming helium nucleus. And so ultimately, that's why we think that the nucleus is tiny, is from this stupid scattering experiment, which made the assumption that all of the charge, in order to do that scatter, must actually be in this tiny center. But if you actually look at pictures, we can see individual atoms now with scanning lane tunneling microscopes, and we can actually see some of the exterior structure of some of these atoms, and they don't. They don't look like a tiny speck in the middle with. They almost look solid, almost like Lego bricks. So, if we ignore the Rutherford scattering experiments and we go with our intuition that atoms are relatively large, that there is matter, in across their entire radius. Then we also have to deal with this question of, how is it that this thing can only be held together by the electrostatic force? Now, the electrostatic force is just attraction of opposites. So proton attracts electron. And so then we'd have to go back to, before the Rutherford did this experiment, there was, say, the plum pudding model of the atom where the protons and the electrons were just more or less mixed into this clump. Now that's much more easily believed, because then if they're all just mixed together, then all the charges would neutralize, and there wouldn't be any need to pack all of the neutrons into this tiny ball, because just that collection of positive, negative charges just interacting with each other would be enough to hold the atom together. But if it was just this blob of protons and electrons, then how do we get what appear to be electron shells? So one characteristic of atoms that it's hard to figure out in that kind of model is that if you knock out one electron, it produces a certain kind of light, and you can knock out 2 electrons, and that comes out. It takes a certain amount of energy to knock that out, and you knock out 3, and it actually forms a very, very specific pattern about the energies that's needed to knock those things out, and there are groups of them, and they group into groups of 2 and 4 and 8. So it'd be very hard to explain how a random ball of positive and negative charges could possibly do that. But I think that the idea of the atom being this ball of positive and negative charges is still a good idea, but it just needs to have some geometric order to it. So I've brought my atomic model here with me today, and it's just made out of Velcro blocks. And so I've got a black block, and that represents an electron, and I've got a red block, and that would represent a proton. So the conventional mainstream says that you've got a proton here, and the electron is effectively doing this. It's orbiting around the proton, but there are a couple of problems with that. First of all, if it was orbiting around, it would continuously radiate energy, and until it ran out of energy and just fell onto the proton. And I don't know what they think would happen if an electron fell onto a proton, but I think it would be just this, that if you have an electron and a proton, and it's not orbiting, it can't really orbit. I mean, what keeps it in orbit? It would stop orbiting, and it would just fall onto the proton. And I don't think this would be any major emergency, or I don't think this would blow up. I don't think this would annihilate. This is not a positron electron. This is a proton and electron. I think the electron would probably just sit on the proton. But this would be hydrogen. This would be the simplest atom possible, hydrogen. And it's not orbiting, and the electron is not orbiting. It would just sit there. So that's the first thing, is that there doesn't need to be any orbiting electrons. The electron can just sit right onto a proton. And I don't know why people have such massive objections to this concept that an electron can just sit on a proton. But the question is so suppose I got another proton and another electron together, and and what would happen to if 2 of these were to fuse together? So you got 2 hydrogen atoms, and what would happen if they would fuse together? Well, I would say that opposites attract. So I would say that they would do this. So if you got them to fuse, they would form, basically a checkerboard structure like this. So this would be helium. And once again, the electrons are not orbiting. They're just stuck in a checkerboard fashion with the protons. Now, this isn't a plum pudding model where these things can take any position possible. They have to take these 2 positions. Now, if you were to ionize off the electrons are still relatively loosely held to this structure, so if you put some energy in, it's going to throw off the electron. although if you manage to ionize off both of these, then it's like it would probably fly apart. So there must be something else in there. And that something else is a neutron. So for helium, you got to have at least 2 neutrons to that thing. So what in the heck is a neutron? Well, a neutron is probably a joined positive and negative charge. So I've got my blocks here. They're both white, but one of them has the positive charge and one of them has the negative charge, so that they come together like that. So, but basically, you could stick a neutron on like that, and actually to make everything balance out. So we've got the two protons here. So I've stuck a neutron in here, gluing these things together. And then I stick another neutron here. So now if I lose both electrons, there's still something holding this together, right? So it's okay to ionize off the 2 electrons, and you still got something that's stable. So I believe that this is actually the purpose of the neutrons, is the neutrons are there to act as the glue for the protons. But this is only held together by the electrostatic force, only attraction of opposites. So we don't need to have any strong force in order to keep the helium nucleus together, even if we ionize off both of the electrons. So this is your first complicated atom, which has neutrons, protons, and electrons. And this does not, once again, there's nothing orbiting in the ground state. I believe that this is all held together by just electrostatic forces. Now, another thing you'll notice that this is very symmetric, and it's a nice cube. And if you were to measure the forces on everything here, they're pretty much at a local maximum. And this is the reason why your noble elements are so non-reactive, because all of the forces within this block are pretty well satisfied. And that all noble elements are actually made up of combinations of helium nucleuses. If you look it up, all noble elements can be seen as combinations of helium nuclei. So we've got, so this is just your helium atom, only held together by just the electrostatic force.
How much space does such a nucleus take, do you think?
Well, this would be, if you just look in the web elements, they'll give you the atomic radius, right, at so many ppm. And so this would take up the entire size, if the size of the stated nucleus was like 10 angstroms or whatever it is, I'm not sure what it is, then this would be 10 angstroms wide. It would take up the entire spot. The atom is not tiny. See, this is the contradiction from mainstream.
Your elementary particles have the size of a complete atom?
Yes, this is the size of this is a helium atom. This is the size. This is space filling the whole thing. Is helium atom.
All your elementary particles have about the size of a complete atom. That's what you're saying. What?
I'm not sure I understand what you're saying.
Now, you have about 8 of these cubes in your hand, and it would. So the size of that thing would be 8 times, 4 times, 8 times the size of an elementary particle, of an electron, for example.
Yeah, for example. Mm-hmm.
Yeah.
But what we're talking about here is actually when you're talking about size of charged particles, it's kind of weird because, what is size? You could think that an electron is must be 1,000 times smaller than a proton, because mass-wise, a proton is 1,000 electrons, right? So you might think that, but from an electrostatic charge standpoint, an electron is exactly the same size as a proton, if you consider size being the influence of its electrostatic field, right? And that's the biggest thing that anything in the region of a proton or an electron fields is the electrostatic charge. So from the standpoint of an electrostatic charge, it is just as big. So it might take up this kind of square geometry, even with the differences in mass. That charge-wise, if you were to get a microscope and look at a helium atom, I would contend that it would look like a cube, like that. It might be. I don't have any evidence of that, but I'm just saying that it might be. Now, if you take,
frankly, why I cannot see? I could not see the charts, the plots that you were apparently showing.
The what? Well, I'm showing
the plots, the graphs, whatever you were putting there. Or did you put something on the screen? I didn't see anything.
It's all in the video.
Okay, okay, good.
Video. So you have to look at my face. And
okay.
On my video. So you'll have to like if you click on my picture, it'll be big. So now if I'm making bigger atoms, then it's all going to be a combination of adding a proton, electron, and a neutron. So basically, this is a deuterium atom. This is like, well, yeah, it's a hydrogen with one neutron. But all of these neatly stack together and fit together, and only one way. This is why I had to invent this model, because it only go together in certain ways, and it's hard to figure out. So that's the only way that that deuterium can attach. So this is the next element up with is lithium, which is 3 protons, 3 electrons, 3 neutrons. Right now, if I were to, you can see that this is not symmetric anymore, right? And you see this showing up in nuclear data, that anything that has basically non-zero nuclear spin is non-symmetric like this. It's lopsided. See, this is actually where that concept comes from. And if you ionize off one of these electrons, this one will come off a lot easier than these ones which are locked into the original helium nucleus. And this is why you see things that look like shells. It's actually a geometric property that as you ionize off these electrons, depending on the position within the atom, you'll get different ionization energies necessary to do that. And so in my model, we just continue on and keep piling on these elements. So this is the next element up, beryllium. So now it has the helium core, but it has 2 ends which are not helium nucleuses. Now this means that it basically forms, it wants to form another helium nucleus here, but what it can do is that it can pick up another. It can form a chemical element with some other, like if this is a hydrogen, so it can attach on. It's looser because generally speaking, it's kind of hanging out here, I think. But it can form chemical bonds with 2 elements, generally in a linear fashion, and that's exactly what we observe. So this is the reason why certain elements form either a triangle or a straight or like 4-way. It's just like if you've ever played with the organic chemistry balls and sticks, that this atomic model allows you to have basically form atomic docking points for other atoms. And this is why they form the particular angle, because it's solid. See, this is a main difference between this model and mainstream, in that this atom is completely solid and can form physical docking points that you can attach things to. But basically that's in a nutshell. Now the thing is that this is all held together by the electrostatic force. So in the case of like carbon to iron, where you would have to basically simultaneously fuse 2 or 3 carbon atoms in an oxygen atom. I mean, how on earth do you do that? Now, my hypothesis on how that works is that the sparking, what it does is that it basically takes this structure and it basically kind of scrambles it up. You know, it kind of loosens it up. And so what happens is that the reason why it forms iron is because iron is basically the lowest energy form of any atom. If you look in the chart, iron is right between the fission and fusion boundary. So what is happening is that you're getting all of these atoms are basically being jumbled up into like this soup. And then when you take away the spark, they all just sit there and they reform back into new atoms. And it just happens that iron is just one of the easiest elements to form. And you'll see that in the distribution of elements on the Earth, you'll see that iron is unusually high. You know, you'll see distribution of elements, then iron is like way up there, and then all the rest, because basically everything is trying to get to iron. So
Yeah.
this is how I feel these kind of fusion reactions are happening.
Yeah, it's another 7 minutes.
There's basically it's basically just messing up these relatively weak electrostatic bonds and then having these things come back together. So that's my short little spiel on my alternative atomic theory that I believe makes things like this this carbon to iron experiment, or even like I was explaining, they were trying to eliminate radioactivity by putting them in a chemical reaction, or by even physical grinding. Because if these atoms are solid, and if you're able to like literally grind off the radioactive part, you could see that happening, because the exterior of the atom is completely exposed if it's solid like that. So perhaps that's how that would happen. But we're getting close to the end of the talk here. So did anyone have any closing comments about my atomic model or about alchemy?
Well, I really can't go too much into your atomic model in such a short time, so it's probably not best not to discuss that anymore.
All right, well, it's something to think about, and maybe we'll discuss it more at our next meeting. So that will be your homework assignment. Think about atomic models, and and we'll discuss a little bit more about whether you think that is right or wrong, or what are the problems with it. There's a book that I have about a whole book on atomic models, and we'll probably be discussing that next week anyways. So
kind of covered that model before quite a bit.
All right, well, to summarize a little bit, so we were talking a little bit about alchemy, which like what seems to be an ancient topic, but we went and we showed that there's a lot of evidence, or at least I know a fair amount of evidence, that there's a different kind of atomic reaction that can go on that can produce these transmutations at a much lower energy than anyone thought possible, and that we discussed that there are some people who claim to be able to reduce atomic waste, and there's people who claim that they are able to make gold, and I showed my own experiment where I produced iron from carbon and oxygen, apparently. And all of these experiments, unless you just want to dismiss them, radically call for a different model of the atom, which just, due to the presence of the strong force, just does not seem to permit these low energy reactions. But as Bill points out, the data shows data is showing that the strong force doesn't exist, that there's no evidence that there's anything like that. And it just, at least in my mind, simply doesn't make any sense that all the protons would be locked together in this tiny little space. And it doesn't really even explain what the purpose of the neutrons are, right? It's like, if the strong force holds together the atom, then what's the purpose of the neutrons? Well, why do they have to be there? I mean, why not just pack the protons in there all and then with nothing, right? But the protons clearly are there to provide some sort of stability. So, and that's why I present my own model, which is just based on attraction of opposite charges. You know, it does show what the purpose of the neutron is there, to keep the atom together, because quite clearly we can ionize off all the electrons out of an atom. And if it was held together by nothing but the protons and the electrons, and as soon as you ionized out all the electrons, that would cause the atom to just fall apart, right? So there must be something holding that atom together, if it's a balanced set of positive and negative charges, which I still think, no matter what model of the atom that you come up with, that is still a good idea, that your atom is composed of nothing but just positive and negative charges spread out in some geometric fashion over the diameter of the atom, rather than this. I'm saying it's a really crazy and bad idea, just based on Rutherford's experiment, to say that the nucleus is this tiny little speck, and that all the electrons are somehow flying on the outside of that, and somehow they maintain their stately orbits and shells for God knows what reason. So, but like I said, I think next week we will probably be going more in depth. We'll probably be covering this book I have on models of the electric thing. So let me give you a preview of that. So let's see here. So this is Models of the Atomic Nucleus by, who's this guy? By Professor Norman D. Cook. So I'll probably send out a reference. This paper is available. This book is available on the internet. So this says, you know, what the previous nuclear models were, you know, like the drop model, and they discuss things about nuclear fission, and what are the problems with atomic models. So your homework will be to you know, take a look at that and see what you think, because that's a pretty good review of atomic history, basically. And then we can come, and this guy has his own version. He calls it the lattice model of that, and you compare and contrast. I know Bill also has a model of the atom, which is different. But we can discuss all those things next time. All right, but that will do it for this week's presentation. So thanks for everyone participating, and I hope that everyone is able to find the link next time, and I'll try and make sure that that link is in enough places and correctly stated. All right, so signing off for now, though.